later, celebrating the half birthday of the Hubble Space Telescope after 30 years. If you're here to see the pretty pictures, you're going to have to wait a little while. There are plenty of pretty pictures, but I'm going to be a little pedantic at first and tell you about why we have a space telescope and, well, what went wrong on. What was so exciting getting from there to here? We're getting here from there. So let's see if I can get the next slide. There we go. So why do we want to put a telescope into space? We have big telescopes on the ground. The biggest telescope on the ground has an aperture of 10.4 meters. The Hubble Space Telescope is 2.4. That factor of 4 is a factor of 16 in light collecting capacity. Why go above the atmosphere? The simple answer is not all of the light that we're interested in observing gets through the atmosphere and gets to us. The slide here is taken from an Astronomy 101 textbook. Visible light gets through the atmosphere. We know that. We can see the sun. Infrared light, some of it gets through the atmosphere, some of it doesn't. But gamma rays, X-rays, ultraviolet, they don't get through. Radio does. We're not talking about radio here. We're not talking about gamma rays or X-rays either. We're talking about the need to see ultraviolet light and infrared light. You can't do that well from the ground. There's light that gets through the atmosphere or doesn't get through the atmosphere we'd like to see. The other thing is that the atmosphere really mucks things up. Even in optical light, the atmosphere is turbulent. Light doesn't come through as cleanly as it does above the atmosphere. And a telescope above the atmosphere can reach what's called the diffraction limit, which is as well as you can focus light. You can get down to a resolution of, well, there's a formula, 1.22 times the wavelength of light divided by the diameter of the telescope. And if you look in visual light and you have a 2.4 meter mirror like Hubble does, that diffraction limit is 0.06 arc seconds, 60 milliarc seconds, which is a pretty small angle. You're pretty much limited to about 1 arc second on the ground. You can do a little bit better, but not too much. So, the history of Space Telescope is that, well, it goes back a long way. There were people who suggested putting telescopes in space in the 1930s. The first formal presentation of the idea came from Lyman Spitzer in 1946, who proposed in a report to Project RAND a space telescope. And it sort of died there. 20 years later, Spitzer, who was then a professor at Princeton, chaired a NASA ad hoc committee called on the scientific uses of the Large Space Telescope. And both of those reports, you can see the first page of the 1946 report on the right. It was reprinted in 1990, but it's from 1946. They said the same things I just told you, that we want to be able to see ultraviolet light that doesn't get through the atmosphere, and we want to take advantage of the superior resolution that you can get in space. In 1972, NASA actually launched an ultraviolet telescope. It demonstrated that, yes, there was really good science to be done in the ultraviolet, but it was only a 24-inch telescope, 0.8 meter mirror. So the history of Space Telescope continues with NASA forming a large space telescope steering group in 1971. They proposed a 3-meter mirror, and it was going to cost up to $500 million in 1971 dollars, which is a lot of money. 4 years later, the proposal got to Congress, who rejected it. It was too expensive, too big. There was no real interest in it. NASA promptly de-scoped it. They took the word large out of the title. It became the Space Telescope, and it became a 2.4 meter mirror. And the estimated cost dropped to about $200 million. And John Bacall and Lyman Spitzer, professors at Princeton University, spent a lot of time lobbying Congress, and they softened up Congress. In the meantime, NASA issued a call for proposals for the Space Telescope. The concept for the Space Telescope is the following. let's put a telescope into orbit. Let's make it a 2.4 meter Ritchie-Chrétien telescope, large focal ratio f/24, so we can get very good spatial resolution. You might say, why 2.4 meters? Well, I'll get to that in a couple of slides. It would work in the ultraviolet, it would work in the optical, and it will work in the near infrared. The plate scale will be 3 arc seconds per millimeter, and if you put a typical detector that was available in the 1970s in there, you could get close to the diffraction limit. The full width half max, basically the diffraction limit, would be 0.04 seconds of arc. That's 0.06 is the diffraction limit. And you could get all of the light from a star, 90% of it, within 1/10 of a second of arc. Your images would be very, very sharp because you have very good spatial resolution. It was designed not as another satellite mission, but as an observatory. The instruments would be replaceable. You could upgrade them. The telescope would last a long time. A lot of parts, there were moving parts on any observatory, they fail. Gyros have a half-life of 5 or 6 years, or used to. So the gyros would have to be replaceable. The batteries degrade, they'd have to be replaceable. The computer, it was anticipated that computers would get better than they were in the 1970s. So the computer was replaceable. The memory was all replaceable. The idea was to minimize moving parts and expendables. There are no reaction jets, rockets on the spacecraft. There's almost nothing to wear out. So it was designed as a long-term observatory in space. And for that cost, you want to keep it up there for a long time. Why 2.4 meters? Well, it would fit in the bay of the space shuttle, and there were lots of 2.4 meter blanks available. The reason is the NRA was building lots of space telescopes that pointed down using 2.4 meter mirrors. These were the KH-10 and 11 satellites. So 2 years after NASA rejected the idea of a large space telescope, they authorized a space telescope for launch 6 years later in 1983. The money started flowing, contracts were let, the mirror was completed and polished in 1981. In 1982, I actually started working on the project as a postdoc out in Colorado. I was working at the Ball Aerospace company for a short time as a part-time job in my postdoc, working on one of the calibration of one of the first-generation instruments. By 1984, the optical telescope assembly had been put together. That means the mirrors were put together in the whole barrel of the telescope. And in 1985, the spacecraft was finally put together. The instruments were all bolted in, and integrated testing started at Lockheed Martin Corporation. The spacecraft was shipped to Cape Canaveral, and in 1986, the space telescope, the Space Shuttle Challenger exploded on launch, and we were stuck. Well, 4 years later, the Space Telescope took off. STS-31 carried the Space Telescope into orbit. It's in orbit around the Earth, the low Earth orbit, 540 kilometer orbit, roughly 28-degree inclination. That's what you get when you launch from Cape Canaveral, from the Kennedy Space Center. It orbits the Earth every 95 minutes. That makes it a difficult observatory to operate. Night and day come every 95 minutes. You don't get 8 hours to observe your target, you get 45 minutes roughly. Shortly thereafter was named for Edwin Hubble, who didn't discover but popularized the concept of the expanding universe. He spent a lot of time in the 1920s and 30s observing what were then considered distant galaxies and showing that the universe was expanding. This is his Hugh Hefner pose with the pipe. We don't smoke in observatories, but I hope this was just a publicity shot. So here's the Space Telescope. This is the optical telescope assembly, the overview. it's a telescope. And if you can see my cursor, the primary mirror is located down here. The light comes in, hits the primary mirror, bounces off the secondary mirror, which is a 0.3 meter mirror, and it focuses down at the Cassegrain focus back here. This is where the instruments are. There are 5 instrument bays. One is right on axis, where you presumably get the best focus from the Space Telescope, and there are 4 axial bays off to the side. The computer is really keeps the spacecraft going. It's really amazing to think of what we thought was a good computer back in the 1970s. It was called the DF224. DF supposedly stood for damned fast. It was a 1.25 megahertz machine with a 386 processor, and it was sped up with a math coprocessor. It was upgraded in 1999 to a 486 machine that ran at 25 megahertz, and that's still up there chugging away. Your cell phone, your smartphone does much, much better than this, of course. But your smartphone is probably not radiation hardened. There were 6 original instruments. I said there were 5 instrument bays. Well, there were really 6 instruments available. There's a faint object camera, which was built by the European Space Agency. They cooperate, that's the right word. They operate jointly with NASA, the Space Telescope. They get 15% of the time for building the FOC. The Goddard High Resolution Spectrograph is the instrument that I worked on for a number of years in the 1980s and 90s. The High Speed Photometer, a faint object spectrograph, a wide field and planetary camera, which was the radial instrument. That's the one that went for the best focus. And then there are 3 fine guidance sensors. Their main role in the telescope is to hold it stationary when it's looking at an object. You don't want this telescope wobbling while you're looking at an object. That sort of destroys the good seeing you can get up above the atmosphere. But you don't need all 3 of them. 2 of them will suffice. Actually, 1 will suffice. And the other ones can be used to study stars that happen to fall in their fields of view, and they could do precision astrometry on select stars. So this was the first light image. This is what the operators on the ground saw a few weeks after the Space Telescope was launched from was thrown overboard from the space shuttle. And it's a rather ugly picture. You see stars there, but the stars are fuzzy and there's a lot of scattered light. The plot on the right shows this curve here with the X on it shows what the profile of a star, what it should look like. It should be sharply peaked. Now here's the peak of the star and it falls off very fast. And you would have, in this case, 70% of the light within less than a tenth of an arc second. And there's always going to be a scattering halo. No mirror is perfect. There's always dust on your mirrors, even in space. But you want, the spec was this, 90% of the light within 0.1 arc seconds or something. Well, this is what they saw. That's not even close to being meeting specs. It's terrible. You can actually do much better from the ground. The problem is the mirror was made incorrectly. The primary mirror, you probably heard this story. And it's a problem called spherical aberration. Spherical aberration is one of the aberrations that affect telescopes to make the light not come to focus. On a mirror, the light comes in. Now, the Hubble mirror is not spherical, but it's the same, same issue. The light coming in far away from the center focuses down here someplace, and the light coming in closer to the axis of the mirror, the paraxial rays, focus up here. So the light focuses somewhere between here and here, depending on where it hits the mirror. It's shown better in this diagram, but this has a lens rather than a mirror. So just think of the light is coming in from the opposite direction, coming in this way and coming out here. From the edge of the mirror, the light focuses down here. from the center of the mirror, it focuses out here. And anywhere between here and here, some of the light is in focus. It's never all in focus, but some of it is in focus. So with the Hubble Space Telescope, when they went to those first, went to this image and they tried to focus the light, they'd move the secondary mirror back and forth, and the image didn't change very much. You always had about 10% of the light in focus, and 90% of it was somewhere else. So that's the problem. There was spherical aberration in the mirror. And of course, the cartoonists went after it. This one says, maybe outer space really is blurry and out of focus. So what went wrong? The mirror was ground and polished at PerkinElmer in Danbury, Connecticut. They had a reputation for doing precision optics. The upper left picture shows the mirror being ground. You start with a flat blank and you grind out a shape because you want to end up with a concave mirror. And on the right is a picture after the mirror had been polished and coated with aluminum. You can see some magnification there. The people appear bigger in the mirror than they do in real life. What went wrong? Well, NASA, of course, put together a commission to study it, and about 6 months after launch, the Allen report came back. And I want to go through this a little bit just to tell you, because there are lessons involved here. The problem with a mirror or any optical piece of optics is you got to test it. You want it to be the right shape. And it's very, very easy to test a mirror for sphericity, to make it a sphere. And it's almost as easy to test a mirror should be a parabola. But the Hubble Space Telescope mirror is fancier than that. It's much more complex because you want to take advantage of being in space. So PerkinElmer designed what they called a reflective null corrector, the RNC, which is illustrated on the right, which was an optical device where you would shine light in and it would bounce off a couple of mirrors, basically a telescope, go through a lens, and it would distort the light coming in such a way that it would make the primary mirror look exactly like a sphere. And then you could polish it and make sure the sphere came out the right shape. The field lens had to be a specific distance away from the primary mirror, and that was set by a rod attached to the back of the field lens, which was positioned using a laser, using laser interferometry. This is important. Now, the end of the rod was polished to reflect the laser light, and it was held firmly in place with a black anodized flange, an aluminum flange. And the black was designed to not reflect light. So it would be located precisely using laser interferometry. Now, it took a long time for the engineers to actually build this. In the meantime, they built a simpler inverse null corrector using lenses, which they also used to test the reflective null corrector when it was ready. When they tested the reflective null corrector, and by this time they had pretty much finished grinding the mirror, it looked like the reflective null corrector was made the wrong way. It had spherical aberration. That was a red flag. But the engineers, the technicians at PerkinElmer dismissed this because they knew that the inverse null corrector was put together rather hastily. It was not going to be nearly as precise and accurate as the reflective null corrector. So they figured the reflective null corrector, which they had spent a few years putting together, had to be correct. Well, assuming that it was correct, they polished the mirror to 8 nanometer RMS. 8 nanometers is about 80 angstroms, or is about 80, the size of 80 atoms. So it's a very smoothly polished mirror. It's in fact the best mirror ever made. It deviates, those of you who are amateur astronomers, it deviates by just about 1/70th of a wave in red light. That's much better than specifications. So while Perkin-Elmer was telling NASA that they were doing a good job and NASA was congratulating them on it, nobody noticed that somehow in the handling, the black anodized coating had been scratched, and the laser was actually reflecting off the flange rather than the end of the rod, and the field lens was mispositioned by 1.3 millimeters. That, it turns out, is why the inverse null corrector seemed to show that the reverse null corrector was aberrant. There are also two less technical items that were pointed out. It took longer to grind the mirror than they had predicted. You predict how much glass should come off the mirror, but they took off more. It took longer to grind, and they just didn't worry about that. And then there's this extensive, this is the executive summary report, which basically says what I just told you. The lessons that come out of this are that there were plenty of warning signs, but the engineers instinctively trusted the more complex and the more expensive instrument, even though it wasn't right. There were time and cost pressures. They were building this thing. They had 6 years to build the telescope. They wanted to get the mirror done first. They had to get the mirror done first because everything is built around the mirror. The mirror had to be done in 1981. They didn't have a lot of time to check it. And they didn't have enough money. NASA doesn't NASA contracts aren't as lucrative as some other contracts. So they didn't have enough money to double and triple check everything. And then finally, the existence of discrepant data was not passed on to NASA. NASA has ultimate oversight authority. They didn't ask, they weren't told. So it was concluded that NASA was deficient in its oversight too. So a lot of things came together here that should not have happened. But we get a lesson out of this. And the lesson is that there is a difference between accuracy and precision. And this is a lesson that you should know well. The Hubble Space Telescope has the most precisely ground and polished mirror ever made for astronomy and probably for any purpose at all. It's the most precisely ground mirror. It just happens it's the wrong shape. It's inaccurate. Fortunately, it's a spherical aberration. It's radially symmetric, and it's easily correctable. In this case, it would only cost NASA and ultimately the taxpayers $40 to $50 million. And it was fixed in 1993, about 3.5 years after launch. In the first servicing mission, the Hubble, the high speed photometer was replaced with COSTAR, I misspelled that, the correctable Space Telescope axial replacement instrument. It provided pairs of mirrors, 2 mirrors for each of 3 instruments. The 2 mirrors, the light coming into the telescope would bounce off one mirror. The light comes in here, bounces off a mirror down here, bounces off a mirror up here, and those 2 mirrors would defocus the light in just such a way that by the time the light went down into the aperture and hit the instrument, that it would look like the Hubble was in perfect focus. We're up to 4 mirrors now rather than 2. You lose a little bit of light, but that's insignificant. But you now have a telescope that is in focus. The wide field planetary camera was replaced with wide field planetary camera 2, which had its own internal optics that corrected for the malformed primary mirror. And this is the result. On the left-hand side, you can see that out of focus image of a star. And on the right, you can see, I presume it's the same star. After COSTAR, stars are point sources. They all more or less look the same in an image like this. And you don't see all of that radial pattern surrounding the star. 90% of the light really is concentrated in that central peak. Below it is an image that shows it's a more complex thing. It's a galaxy. I think it's M101. And on the left is an image taken with the pre-COSTAR, and it's fuzzy. It's obviously fuzzy. Now, if you compare it to an image taken from the ground, it's really not that bad. The stars are sharper than you can see from the ground, but it's fuzzy when you compare it to the after CoStar picture on the right. I think you'll agree that the picture on the right shows an awful lot more detail than the picture at the left. And here's another picture, the nucleus of a globular cluster. The picture on the left shows lots and lots of stars. All the stars are surrounded by halos, which is the scattered light from the stars. But you can actually do some good science. You can count the stars if that's what you want to do. And this is an ultraviolet light. You can't do this from the ground, so this is unique science, even pre-CoStar. On the right-hand side, you see the same image. Basically, it's a slightly different filter, but the stars are much clearer. You see many more stars. You don't have the scattered light. You see a darker sky. So the mirror was fixed. It only took 4 years and $40 million, but the mirror was fixed. And as of 1993, the Hubble Space Telescope was meeting specs. It was better than it was supposed to be. And of course, the editorial cartoonists made light of that too. Well, there have been a number of servicing missions. The instruments have been upgraded. It's been dealt with like a real observatory, where when instruments get better, you replace them. The Space Telescope Imaging Spectrograph was installed in 1997. The instruments in red are still working. And the gyros and solar panels were replaced, and they put in solid state memory. In 1997 and 2002, the servicing mission was split into 2 parts. They put in a new computer. They replaced the gyros and solar panels both times. They put in a new imaging instrument, the Advanced Camera for Surveys. They didn't need CoStar anymore, so they could take that out. In 2009, the last servicing mission, the 5th one, the Wide Field Camera 3 was put in the radial bay. They put in the Cosmic Origin Spectrograph. They repaired 2 instruments. The instruments were made to be fixed in space. Both of those had failed in part, at least, and they were correct. They were fixed by the astronauts. It was about a 7-day mission, I believe. They had a lot of things to do. They replaced the fine guidance sensors. They replaced the gyros, the solar panels, the batteries. The thermal blankets, these are those silver mylar panels covering the spacecraft that help it maintain its temperature, reflecting sunlight. Well, they degrade after 20 years in orbit. So they were all replaced. So it was a brand new spacecraft in 2009, brand new telescope, and they actually added a what's called a soft capture mechanism to the back of it, so that if NASA wanted to do anything with it in the future without access to the space shuttle, they could grab it. So this was one of the last pictures that's been taken of the Space Telescope. This is it in the Bay of Atlantis in 2009, looking very spiffy. This is the configuration of Hubble today, showing the 4 axial instruments down here, the radial instrument up in the front here, 2 solar panels, and all of the other things that make a telescope function, the secondary and the primary. Basically the only parts on here that are original are the mirrors. You don't replace the mirror in orbit, and the structural elements. But all of the instruments have been replaced. This is what you see when you look down the barrel of the telescope at the mirror. Light that goes right down the center hits the Wide Field Camera 3. And if you want to put your star in where you can get a spectrum with COS or a spectrum with STIS, you have to move it slightly off axis. These are distances in seconds of arc. The ACS is here. There's nothing here because Nick Moss is no longer operating. That was by design. So it's got 4 functioning instruments, and the fine guidance sensors, FGS, are around the outside. And for those of you who are interested in technically what it can do, it does spectroscopy and it does imaging. Spectroscopy, we concentrate on the ultraviolet, but we do optical spectroscopy too. Imaging, optical, UV, infrared. The field of view is small. It's 2 arc minutes by 2 arc minutes. The moon is 16 arc minutes across. The wide field camera is 3 arc minutes actually. But you have very good spatial resolution, 30 milliarc seconds in the ultraviolet. Actually 25 milliarc seconds in the ultraviolet here. And the wavelength range, it actually reaches down from almost into the far ultraviolet all the way to the infrared. So that's what you can do with it. So it's a functioning telescope. It was last refurbished 11 years ago. It was new at the time. It's still functioning well. Nothing has failed. NASA did a very good job planning this. The astronauts did a wonderful job refurbishing everything. There are no more servicing missions planned because there's of course no more space shuttle. It's planned to operate at least through the commissioning phase of the James Webb Space Telescope, which will be launched someday. It's always a year to 2 off, but maybe it'll be launched towards the end of 2021. And after that, it depends on the budget. If everything keeps working, it will be a pity to turn it off. The orbit, well, the orbit has been raised 5 times each servicing mission before they let it go. They actually boosted it up in orbit by another 5 or 10 kilometers because even at 540 kilometers, the orbit decays with time. The orbit is stable for the next 10 years. It will not re-enter. This depends on solar activity. We're in a minimum of solar activity now, maybe a long-term minimum, but that's another story. And if we get another solar maximum starting in the 2030s, that will make the orbit decay. We don't want it to re-enter. It's rather heavy. NASA does not like liability issues if they can avoid it. So the soft capture mechanism that was installed will allow NASA to put a rocket, attach a rocket to the back of it, and either deorbit it into the South Pacific or to move it into a higher parking orbit where it can be recovered later on. There's always been talk about, let's put it in the Smithsonian. It's been such a wonderful instrument, but that's a ways off. So now that you've sat through my pedantic lecture on the lessons of the Space Telescope, let's talk about some science. Let's look at some pretty pictures. All of these pictures are available at the Hubble site, hubblesite.org. You can get to it by Googling Hubble Space Telescope. There's a very large public relations team down there, and they do a wonderful job selling the science, and in the hopes that you and people like you will go to your congresspeople and tell them we have to keep funding astronomy. We have to keep funding things like the Hubble. Look at the wonderful things it does. So this is a color image reconstructed, false colors, of part of the Carina Nebula. I could spend probably hours pointing things out in here. Well, not hours. I won't. But you see some interesting dark clouds here that are lit on the edges. They're backlit by bright hot stars off the field. The blue stuff is gas. This dark stuff around here is dust. You see these pillars sticking out. We'll see better pictures of pillars in a moment. All these little white dots are stars. They're foreground. They're between us and Carina, which is off at a few thousand light years. This is one of the prettiest pictures, I think, they've processed and publicized. All of these data are heavily processed. What you get back from the instruments are counts versus pixel. It's a black and white picture. So you take pictures in many filters, you combine them, you stretch them, you use false colors to bring out what you want to see. This is NGC 2014. It's a nebulosity. There's actually a cluster of stars in here that's burning its way out of this dark, what was once a dark cloud. Now it's mostly gaseous, but there's dark parts down here in the back. I'm not quite sure what this is or whether this is related to the cosmic reef, but it makes for a very pretty picture. You can see background stars here. There's a lack of them around here. That means there's some dark dust in there. There's a little nebulosity here, which is almost certainly related to this. And this nebulosity down here, there's a star inside there illuminating it. There's a wealth of science here, which we're not going to go into. These are some of those dark clouds, the elephant trunks, they sometimes call them. This is in the Carina Nebula. This one somebody has called the Mystic Mountain, and NASA likes that name. It is stuck. So there's this dark tendril of dust. It's been evaporated from the outside by hot stars that you don't see. Here's a dark tendril of dust that's glowing at the top. There's a star in there trying to get out. The star is being born in the dust, in the clouds of dust, and it's evaporating cloud from the inside out. Anything with diffraction spikes is a bright star. The stars here mostly have nothing to do with this cloud of dust. And you see here at the top, there's a star in here trying to get out, and there is a jet of material coming out, two jets in two directions. There's a bow shock because the stuff being blown out, blasted out in this jet from the star is interacting with the interstellar medium, with the stuff left over from the evaporating dust cloud and forming this bow shock. Much like a boat going through the water, it makes a wake. There's another nebula. It's called the Monkey Head Nebula. This is only a little part of it. This is a very small part of a much larger nebula. These nebulae are many arc minutes across, sometimes degrees across. The Carina Nebula is huge, but this is only a fraction of an arc minute across. I don't know exactly which camera took this, but you see fine details. The deeper and deeper you go into this picture, the more details you see. This is another case of stars being born in these pillars of dust. There was a famous picture, which I'm not going to show you, called the Eagle Nebula, the Pillars of Creation. But one of those stars is, of course, it disappeared. Yeah. One of them is up there, just in the upper right. Here's my cursor. Right here, there's one of these stars being born at the edge of this filament of dust. You may know of this, the Horsehead Nebula. This is the Horsehead Nebula seen in infrared light, so you can actually see into it. In infrared light, it's not opaque all the way through, not all of it, so you can see stars in the background. And you can see that this is a complex three-dimensional structure. It's not just a black horsehead shape superposed on the background sky, but you can see here at the bottom, these pillars are illuminated from the top by, well, probably by these two stars. And you can see all the three-dimensional structure in here and a star forming at the tip of the horse there. Here's another young star. This is almost a surreal image. The star is at the center of this dusty area. It's called Herbig-Haro Object 24, and it's spewing out this cloud of these two jets in opposite bipolar flows in two dimensions. In two directions. This is how stars form. When a star collapses, it's rotating, and it has to get rid of this excess rotation, this excess angular momentum, and it dumps it into these jets somehow, and they get blown off into space. In the meantime, it's clearing out the cavity here and a cavity here, and eventually the star itself will burn away the dust here, and you'll be able to see a young star. You can see lots of neat things in these pictures. This looks like a series of, well, something you might get off an Etch-a-Sketch, series of concentric rings. This looks almost like a fish down here. Globular cluster, this is what you get after you make these stars and you wait 10 billion years from the ground. This is a very distant and faint globular cluster. There's a million stars, and the size of the cluster across here is something like 10 light years. Very, very dense. You can't see all of this structure from the ground, but from the Hubble above the atmosphere, you can peer down into the center of the cluster and actually count stars, see if there's a cusp at the center. Is there a black hole that's at the center of this particular globular cluster? The red stars are really red stars. They're red giants. The blue stars are younger. I think the blue is exaggerated because all of these clusters are old, but the blue is main sequence, older, is more massive main sequence stars. This is not a globular cluster. This is a massive cluster of massive stars. Here at the center, it's called Westerland 2. Here at the center is a million solar masses of stars. There are a couple of stars in here that are about 100 times as massive as the sun. They will explode within a few million years as supernovae, if you want to wait around that long. In the meantime, there are thousands of other stars forming in here, probably 50,000 stars altogether. They will disperse out into space over time, and you won't recognize this area after those supernovae go off. All of this gas that they formed out of will be blown away, and the stars will just spread out throughout the Milky Way. The Tarantulam Nebula in the Large Magellanic Cloud contains probably one of the most massive stars known. Ultraviolet spectroscopy, the plot down here in the lower right, shows what these stars look like if you take a spectrum, if you disperse the light in the ultraviolet. What you see is that these stars have emission lines from oxygen 5, nitrogen 5, carbon 4. These stars are 30 to 50,000 degrees, really, really hot, much hotter than the sun. The sun's only 5,760 degrees. But these stars are 50,000 degrees or thereabouts. And they're losing mass. This dip here, you go to the ultraviolet to see, you can't see this in the optical. This is matter being blown away from the star. It's being blown towards you at velocities of hundreds of kilometers per second. These massive stars lose an awful lot of mass before they explode as supernovae. This is the Bubble Nebula. This is one of those sort of little ephemeral things. It doesn't look like it could be real, but it is real. This is a wind-blown nebula. There's a star somewhere at the center here. I don't know which star it is. Might be this one, might be this one. Neither one's exactly at the center. That's blowing a wind, and this is what's left over. It's an H2 region, actually. And this is this is hot gas illuminated by a star from its ultraviolet radiation. From the ground, it looks like a little dot. It's not much of a bubble. And you can see off in the corner here, there's more of those little pointers of dust with stars forming. The dust is being evaporated from the light from this hot star. We look at remnants of stars too. Eta Carina, one of the most massive stars in our galaxy. It's actually two stars orbiting each other. It looks like two heads of cauliflower because these stars are losing mass. They're orbiting in this plane here. In the 1860 something, this was the second brightest star in the sky. It's quite a bit fainter now. It's about 6th magnitude. And you can see all this fine detail of past explosions. We don't know how the star is going to end up. It's probably going to turn into a supernova. It could happen tomorrow. It could happen in 10,000 years, or it could happen in 100,000 years. But there's about an 80 solar mass star buried in there, and we can study the dynamics of how it is dying. The Crab Nebula, we knew all about the Crab Nebula before. You get some wonderful pictures from space, from X-rays and from Hubble. We get this wealth from the ground. This was a supernova, 1054 AD, and this is a composite picture. The yellow and the red is from the Hubble, and you can see this fine filigree pattern. This is a star that blew itself up, and that's the remnants of the star streaming out into space. On the left is another supernova. Well, this is not a supernova remnant. This is it's a planetary nebula. It's called the Southern Crab because it looks like a crab, at least a crab with 4 legs. And in the center is a bright star. That is an ultraviolet, bright, very hot subdwarf, it's called. And it's illuminating these rings of material, which is material it blasted off. It blew off, I should say, gently, when it was a red giant star not so long ago. And today, that red giant, the core of the red giant has become this hot subdwarf. It's on its way to disappearing from view. But you see, this is the most recent ejection to material. This is stuff that was blown out much, much longer ago. I got to throw in, plug in myself in here. This is my only PR shot from the Hubble. We observed the neutron stars zipping across the sky. It's a mere 120 parsecs, 360 light years away. It's moving at 100 and some odd kilometers per second. It blew up about 1 million years ago, and the idea was to measure how fast it's moving, what is the wobble in its motion due to parallax, which we did successfully, and to try to figure out its size, which was hard to do, and we still don't know. It's about 12 to 15 kilometers across. Not very big, and not very bright. This is 25th magnitude. If you're an amateur astronomer, you know that you probably have never seen anything fainter than 20th magnitude in your camera's 15th magnitude by eye through a telescope lens. This is 100 times fainter than that 20th magnitude object, 10,000 times fainter than that 15th magnitude object you might be able to see through your telescope. Closer to home, the upper picture is Europa, taken with the Space Telescope. These are almost as good quality as we got from the Galileo spacecraft, which was in orbit around Jupiter. On the left is the true color picture. On the right, it's enhanced to see some of these streaks. Europa is the smoothest object in the solar system. Saturn infrared light below shows structures in the clouds. And Jupiter with Io casting a shadow. Io is about the size of our moon. You can see the detail that you can get. This is 4 astronomical units minimum from the Earth. We don't only look at planets in our own solar system. With the Hubble, we can look at planets outside the solar system, exoplanets. We can do spectroscopy on these exoplanets and see what their atmospheres, if they have atmospheres, and if they do, what they're made of. On the left are spectra in the infrared showing absorption by water in 3 exoplanets. These dips in the spectrum here and here show the presence of water. The red is the model. The blue are the data points. Yeah, the model always looks better than the data. These are faint. In fact, what you're doing is you're watching this planet go in front of its host star and seeing light being absorbed. You cannot see water in other planets because there's water vapor in our atmosphere, or I should say you can't see it from the ground. You have to get above the ground to see this. And on the right, there's methane in the atmosphere of this star. There was probably methane in the atmosphere of the Earth very early on. Further out, you all like to see pictures of galaxies, I'm sure. Here's a barred spiral, NGC 1365, showing a wealth of detail. You don't see the spiral arms. They're too big on this scale. But what you see is the central bar here. The arms start down here and up here. The dark stuff is dust lanes in the bar and the spiral arms. These get messy if you try to count them. Are the 3 arms on this side? Are these real arms or sub arms? I don't know. This ring around here in blue is recently formed stars at the outer edge of the bar. The only spectrum that ever made the front page of the New York Times is shown here. This is from 1997. This is a spectrum taken with STIS, and we're looking at a galaxy called M84, and we're looking at gas. This is where the spectrograph was pointed, and we're looking at gas, and the gas, the velocity of the gas is low on one side of the galaxy and a little higher on the other side, but close to the center, it becomes very blue. It's coming towards us very fast, and immediately becomes very red, going away from us very fast, and it spins down. What causes the velocity to go way up so fast? There's a black hole in the center of this galaxy, and by measuring the velocity of the gas as a function of distance from the center, you can measure the mass of the black hole. This has a black hole that's about 1 billion times the mass of our sun, 1,000 times the mass of the puny little black hole in the center of our galaxy. Galaxies are fascinating. They interact, they collide. This is a pair of galaxies called ARP 273, and the lower galaxy, both galaxies are distorted. This lower galaxy is distorting the upper one. This spiral arm is being pulled out by the gravity of this one. You see tendrils of stars being pulled out here. Studying these gives us an indication of, well, the dynamics of the galaxies, and we can estimate that in 1 billion years, there's going to be one galaxy here, not two. And I'll end on this picture. You've probably seen this before. This is the deepest picture Hubble ever made. This is the Hubble Extreme Deep Field. They made a deep field, they made an ultra deep field, and this is the Extreme Deep Field. This is about 100 days worth of data co-added, and everything you see in this picture, with a couple of exceptions, is a distant galaxy. You see right here, that's a star. It's got diffraction spikes. There's a star here. It's got diffraction spikes. And the red and blue are oriented differently because those images were taken at different times. But everything else in here is a distant galaxies. These tiny little things here are galaxies when the universe was less than 1 billion years old, when the galaxies hadn't formed fully. You see big galaxies. Here's a regular size galaxy a long ways away from us, but these little things are pieces of galaxies that over time will merge into bigger galaxies. So the Hubble is a wonderful observatory. It's lasted for 30 years. It's going to last a few more, hopefully many more. It lets us observe everything from nearby planets. We've observed Mars, all the way out to the distant edges of the universe and everything in between. And it shows no hint of slowing down anytime soon. So I will stop at that point. I've probably gone about 12 minutes too long, but I will be happy to take any questions you might have.
We have, looks like in the chat, I'm just going to we have a question. What is Project RAND?
Project RAND was a think tank that worked for the Department of Defense after World War II. And I don't know if they're still in existence. I know in the 1960s they put out reports on UFOs, but they're a think tank. They do whatever the government asks them to do.
We have, do all the sensing instruments work in parallel?
They can. At least 2 can work at a time, and I believe 3. They cannot all look at the same object because they're getting light from different parts of the telescope mirror. So you will have a primary target that you point whatever instrument you want at, and then the parallel instrument can be taking data, usually just doing imaging, at a place a few arc minutes away in the sky. And a number of these images of distant galaxies have been built up using those kinds of observations. You do a spectrum of a star, and you point. There's always galaxies somewhere else, so you get basically twice as much observing time as you are awarded.
We have, what future does the James Webb Telescope have?
Well, we first of all, we need to get to the present. It's still on the ground. I don't know what the current update is. I believe it's supposed to be launched late in 2021, which is only a year from now. So we're the closest we've ever been to launch of the James Webb Space Telescope. I should point out the James Webb Space Telescope is not a replacement for the Hubble Space Telescope. This is not a serviceable mission. It's not an all-purpose observatory, and it works in the infrared. It does not do ultraviolet or optical astronomy. But it will extend things out to longer wavelengths. It's about a 5-year mission. It doesn't have, it can't be repaired, things can't be replaced. It doesn't have expendables either, but you expect that, NASA always puts a guarantee. It is guaranteed for basically 5 years, and then we'll see what happens.
Let's see. This one's a nice one. How is the Hubble kept clean?
Who said it's kept clean? It's up in space, and solar ultraviolet radiation and collisions with charged particles in the Earth's upper atmosphere, mostly oxygen, take a toll. You don't point the telescope directly in the direction that it's orbiting, because that will harm the mirror coatings. The thermal blankets degraded considerably over 20 years. They've all been replaced. So in another 10, the Hubble will start showing its age again. You launch something that's fairly clean. There's no dirt in space or anything like that, but you get micrometeoroid impacts. There may be little holes in some of the solar panels and the thermal blankets, but they probably gave it a good dusting before they took that picture in the Hubble, in the shuttle bay of the Atlantis.
How do they decide what the Hubble will look at?
Complicated question. Good question. We professional astronomers dream up things that we want the Hubble to do. We write proposals. The proposals are collected once a year. They're sent to NASA, and NASA convenes a review panel to read the proposals. And every year, the telescope is oversubscribed by about a factor of 15, 12 to 15. So many of us are disappointed at the end of the day. But these review panels make use their judgment, peer review, to say which is the most compelling science, which is the most important science, which is the best science that Hubble can do. And they will send this list on to NASA, and these targets will get scheduled by the schedulers at the Space Telescope Science Institute. It's been working very nicely for 30 years.
Let's see, we have how long will the original, how long was the Hubble originally expected to be functional?
I believe the original expectation was indefinite, because it was meant to be serviced with all the parts replaceable. And this is 1975. The space shuttle hadn't flown yet, and there was no expectation that it would stop flying at some point. So I don't believe that NASA put an expiration date on the telescope.
Let's see. What role do you see private companies such as SpaceX playing in scientific research along with commercial projects?
Unfortunately, not a lot right now. Commercial industries were much more into doing science in the 50s and 60s, even into the 70s. Lockheed, before it became Lockheed Martin, did a lot of good science. They still have a solar division that does some solar science. But for the most part, science hurts the bottom line. You don't get much of an investment on return in basic science. So companies are not doing this anymore. It's unfortunate. There's a lot of expertise there, but the shareholders don't want it.
Let's see. We have a question. Were you shocked by the deep field image of what was thought to be empty space?
Can you say that again?
Were you shocked by the deep field image of what was thought to be empty space?
No. Every time we pointed a bigger telescope at a part of space, we see new things. So it was expected that if you point the Hubble at a place in between stars, in between known galaxies, you'll see more stuff. The scientific question is, does it stop at some point? Is there an age beyond which there's no visible light in the universe? Have we seen the oldest galaxies? We haven't gotten there yet. But we do see galaxies getting smaller, and we get fragments of galaxies. So there's some interesting science in that. But my guess is that if you build in part the James Webb is going to do this. It's going to look in infrared light with a bigger telescope. It's a 4 meter, I believe, and it will look at galaxies that are even more redshifted, so you can see things that are further away, and we'll see when the first galaxies formed and how did they form. Did they form around black holes, or did they form and then black holes form in the centers of galaxies later? There's a lot of questions out there, so we're not even close to seeing the most distant things.
Well, this one's a nice. What do you suggest as a good telescope to use for home use, like someone who wants to set up the telescope on their deck? And
yeah, I got that question yesterday from a colleague of mine in philosophy, and the problem with investing in a good telescope's going to run a few $1,000s. If you're a dedicated amateur, buy yourself a good quality 8-inch telescope, something you can put in the back of the car and take to a dark site. If you don't know if you want to invest in this, don't know what you want to look at, 2 options. One, get a good pair of 7x50 binoculars. If you lose interest in looking at the sky, binoculars are good for other things too. But 7x50 binoculars, you can see planets. I mean, get a tripod too, so it's not you're not depending on your arms to stay steady and steady the image. But you get a wide field of view. You can see nebulosities, you can see star clusters, and you can just enjoy the night sky. If you want an inexpensive but good telescope, I forget the name of it, but the Astronomical Society of the Pacific has a shop, and if you go there, look for telescopes. There's a little telescope that it's I believe it's a Celestron. It's a starter telescope. It costs like $60, and it's lightweight, portable, and you can try that out. And there's any range in between. If you're going to invest and buy a telescope, get a good one. Get one that's going to last. Get one that has good optics. Read reviews in Sky and Telescope or Astronomy Magazine, but don't get a cheap telescope.
we have, it looks like Jane has her hand raised. You could ask your question, Jane.
Can you hear me?
Yep,
I can hear you.
Oh, what's the possibility that Hubble could run into other satellites or debris floating around Earth in space?
It's always possible. NORAD is tracking lots and lots of stuff up there. It's hard to move the Hubble because there are no reaction jets. I know the space station has to move frequently out of the way of things. Um, if you're on a collision course with something, the protocol, I do know this, is you close the aperture door so nothing gets into the telescope mirror, and you turn the telescope around so the backside is facing wherever this thing is coming from. And it's not going to hurt the telescope itself. It may ding one of the instruments or something, but there's some padding back there. But let's hope it's in a pretty clear orbit.
We have a question from MP. Okay.
Yes, hi. Yes, hi. Thank you so much. This has been a great presentation. And a couple of years ago, I got to meet Mike Massimino at an Explorers Club program. Anyway, my question is, what's the difference between what the Hubble can see and what the telescope that's being built in Chile will be able to see?
Are you referring to the Large Synoptic Survey Telescope?
The one in the I never pronounce it, the Athabasca Desert, the
Atacama Desert.
Anaconda Desert, that's it.
Okay, that may be a different one. That may be the ALMA telescope. There are many telescopes down there. I'll mention, so I'll go through these two. ALMA is a sub-millimeter telescope. It's an interferometer. It's like 60 telescopes. It's basically a radio telescope, and it's used to study dust, basically, and in other galaxies and in star-forming regions. Very completely different wavelength ranges. They're highly complementary. The LSST is an 8-meter optical telescope that's going to survey the entire sky roughly every 3 nights, hunting for transients, things that explode, distant supernovae. It will be used, well, there will be people proposing to use Hubble to follow up on things that the LSST discovers. You don't really, there are 2 kinds of astronomy you can do in very broad strokes. One is discovery science, where you go out and you sweep the sky with your binoculars looking for a new comet. Lots of amateurs do this, and you discover new comets or new asteroids. And that's not what Hubble does. Hubble focuses on specific things, but if you discover something some other way that is interesting, then you can propose to use the Hubble to follow up on it. And if it's something really interesting, like a transient, a new supernova, a star being ripped apart and falling into a black hole, where you don't have a year to write your proposal and get it accepted and scheduled, the Hubble can do like a 7-day turnaround, sometimes even a bit faster on these targets of immediate interest. So we all work together in astronomy. We all observe different things and we all talk to each other, and we tend to cooperate.
What was your greatest aha moment in your career viewing the skies?
In my career, I don't know. You don't really get aha moments. Things finally dawn on you. Say, "Gee, I should have seen that 2 years ago." I think the thing the 2 discoveries, let's say, that I like best are the discovery of a class of pre-main sequence stars, what the sun was when it was 1 million years old, that I call the naked T-Tauri stars, because they're stars that are very young, but they're not surrounded by clouds of gas and dust. They're not as photogenic as some of the pictures I showed you earlier tonight. The other was that neutron star, which was a chance discovery. I was not looking for it. I was studying young stars in a particular part of the sky, and here's this really bright, soft X-ray source down in the corner of the image. And it turns out that was a previously unknown neutron star, the closest neutron star, the closest non-pulsing neutron star to the Earth. So those are the 2, I guess, aha moments, but neither one happened instantaneously.
Does anyone have any other questions before we close this evening?
Can you hear me?
Oh,
Yes.
All right, I have a question. So how is it that the James Webb Telescope was not designed to be serviced? I know distance is a big factor, but obviously the servicing that took place during Hubble's lifetime was absolutely crucial to its success.
There are two reasons here. The first is that we don't have the space shuttle. We do not have the capability of servicing it, and NASA decided it was way too expensive to maintain that capability merely for astronomy. The other thing, though, is scientific. James Webb Telescope is not going to be in low Earth orbit. It's going to be orbiting the L2 Lagrangian point. That's 1 million miles from the Earth, away from the sun. By putting it out there, you can, well, you don't have day and night every 95 minutes. You can work continuously 24 hours a day. You look away from the sun. You don't have the thermal issues of orbiting the Earth. The Earth is big and bright and hot. And if you're 1 million miles away, it's small and not so hot. So it's easier to keep the telescope cool. When you're working in the infrared, you need to keep your instruments cool. And that is going to help with the lifetime of the spacecraft. So that's the scientific rationale for going to the Lagrangian point. It has no expendables like the Hubble. So in principle, if nothing fails, it can go on forever. But you know, things will fail.
Thank you.
But I will say we're getting much, much better at building things that don't fail.
Let's see. We have a lot of thank yous. It was an excellent presentation. And Donna McCormick from the Hamptons Observatory just has a thank you in there. I would like to thank Professor Walter for an excellent presentation. And the East Hampton Library also thanks you for being able, in the switched platform, because originally it was going to be in person in the Baldwin room, but we made the adjustment pretty well. Everybody's gotten used to this format now, and I thank everybody for being able to zoom in, and we look forward to more pictures from the Hubble and more great photographs from any of the modern telescopes out there, because we're always interested in space research. And I'd like to thank everybody and have a great evening.
And thank you all for your continued interest in astronomy and science.
Have a great night.
Good night.
Bye-bye.
Thank you.